Alright, so let's start from where we left off in the previous video, which is this theorem. This is the key theorem about nilpotent linear transformations. So before we start the proof, let's again briefly see. We have seen the statement once, and let's just see once more what it says. So we have a nilpotent transformation T here on a finite dimensional vector space V, and it has degree of, perhaps I should not say degree because the word index is being used here. Actually degree is also used, but the author says index, so let's just call it index. Index of nilpotence is n1. What does it mean? It means that the n1th power of t is the zero operator, but the n minus 1th power of t is not the zero operator. That's what it means. And n1 is a positive integer. Then there exists a basis of our vector space V in which the matrix of T is going to have this form, which is a block diagonal form, in which we have these diagonal blocks and we already know what these blocks are. For example, the block Mn1 is itself an n1 by n1 matrix, or more accurately, it's an n1 by n1 array, where all the entries are 0 except the ones on the super diagonal, which are all 1. And the other m's are also like that. And these n's are going to appear in this manner. They are going to be following a decreasing, but possibly decreasing. Okay, some of these may be the same pattern, and the sum of all these n's should be equal to the dimension of the underlying vector space. Now the proof is somewhat lengthy, and the author has divided it into two parts. In the first part, we are going to prove something which is not really very tough, but then the proof continues in the form of a lemma, which we won't see today. I mean, we will see the statement of the lemma, but we won't prove that lemma itself. And we will do it in the next video. So in today's video, what we are going to achieve is we will get this part of the matrix, this Mn1. So let's see how the proof starts. The proof is actually going to start with this condition. So we are going to make use of this immediately. Since this is non-zero, there exists a vector V, itself also non-zero, in V such that when you apply this on V, this is not equal to 0. Well, non-zeroness of this operator tells us that at least it will be non-zero somewhere, right? Because otherwise it is 0. So let that somewhere be this input V, which obviously is going to be a vector coming from V. Now, since the image of the 0 vector under any linear transformation is 0, so that is why, because we want this to be non-zero, so V itself should also be non-zero. All right. Now, we are going to claim something about this V. We claim that these vectors v, vt, vt square and so on all the way up to this are linearly independent over F. These are after all vectors in our vector space V, and we are now claiming that these are going to be linearly independent over F. So how do you prove linear independence? You will have to consider a linear combination of these vectors with scalars coming from the underlying field, of course, and you set that linear combination equal to 0. You will then have to prove that all the scalars involved are 0. So accordingly, let alpha 1 v plus alpha 2 Vt plus, let me write one more term, plus alpha 3 Vt square, and like that it will go up to alpha n1 Vt to the power n1 minus 1 be equal to the 0 vector where these alphas are coming from the underlying field F. Our aim is to prove that all the alphas are 0. Suppose that's not true. Suppose all the alphas are not 0. That means there are non-zero alphas. We don't know which ones are non-zero, which ones are 0. But in any case, you will encounter a non-zero, if you start from this side, like alpha 1, alpha 2 in the natural order in which they are appearing, if you start looking at the alphas like that, you are going to encounter a non-zero alpha for the first time somewhere. Okay, so let S be the smallest index such that alpha S is non-zero. That means the alphas that appear before alpha S in this list, in this order, are all 0. So the terms which have those alphas that are 0 are going to vanish. We are going to have this then. Alpha S V, you may get confused with what the exponent here is and what the index here is. Note that the exponent of t is 1 less than the index. That means here we are going to have s minus 1. The author could have chosen to index this alpha starting from 0 instead of 1, but for some reason he chose to index them like this 1, 2, 3 and so on instead of 0, 1, 2. But anyway, whatever that is, let's just continue writing this thing. alpha s plus 1, let's write one more term, v t to the power s, and so on, plus here of course we have alpha n1 v n1 minus 1 equal to 0. Or now we can do one thing. We can write this sum slightly differently like this. Alpha s, okay, no, we cannot take alpha s outside because it may be just any scalar. Instead, what we do, we take v t to the power s minus 1 outside. You will understand what this outside means and write like this. Should I write just this line or should I write one more line before writing this line? I think that would be better. Let me just show one more line in which what I do, I write this sum like this: v alpha s t to the power s minus 1 plus alpha s plus 1 t to the power s plus alpha n1 t to the power n1 minus 1. Did you see what I did here? You see, there is a difference between this plus and this plus. What is that difference? What is this term? Before you forget about everything, what is this first term? What does it actually mean? We have applied the operator t to the power s minus 1 on the vector v. So the result is again a vector. And that vector we have multiplied with the scalar alpha s. That means this first term is a vector in our vector space V. Just like that, the second term is also a vector. So this plus that you see here is our vector addition in our underlying vector space capital V. This plus, however, is different. This is the plus that we have in the algebra A of V. Addition of two operators or two linear transformations, it is that plus, where we are multiplying the operator t to the power s minus 1 by the scalar alpha s, which also is a well-defined operation. We multiply this one by alpha s plus 1. So these terms now are operators and this plus is their plus. Now if you go back to the definition of the operations of vector addition and scalar multiplication in this algebra, you will see that applying this entire operator, this linear combination on the vector v actually means this, where we have used both the definition of multiplication by a scalar in A of v and addition of two objects, two operators in A of v. That is why this equals this. Okay. Yeah, now we are going to write what the author has written after this. Sometimes going through this type of proofs from whatever text you are using, you may just end up going really fast, forgetting these intermediate things, and then when something goes wrong, you are lost. That is why it's better to really take time and go slowly if you have time. Okay. You see, just understand each and every bit of information carefully, and then only when you are fully convinced, yes, I have understood, then only you move forward. Otherwise, you stick there only. Or, now what does this mean? Now that we have separated this V, we can manipulate this operator itself. What we do, now we are going to take something common out. And that something is t to the power s minus 1. We can do so because the other terms have higher powers of t. And we will be left with alpha s plus 1t and so on. And finally we have n1 minus s equal to 0. But can we do that? Can we just simply take something outside like this? Yes, we can. Why? Because our algebra A of V is after all a ring, and in a ring we have our left distributive law, whose extended version we have used here. Or you can view it like this also. You can multiply this sum from the left side by this operator, and in doing so you are using an extended version of the left distributive law. That's what we have done. Alright. Now note that alpha s is non-zero, and now you recall a previous lemma that we did, I think, in the previous video. Whenever you have a nilpotent operator t and you consider any such linear combination of powers of t where the constant term is non-zero, then the linear combination is regular, it's invertible. That was that lemma, and it was lemma 652. Now, since alpha s is non-zero, the operator n1 minus s is invertible or regular, anything you can write. So what you can do, now that you know this is invertible, you can multiply both sides of this equation, or perhaps I should not say multiply but apply, because we are talking about operators. No, you think of this combination as an operator. It is an operator and it has an inverse. So on both sides of this equation you apply that inverse. On the right side you will apply that inverse on the zero vector. So you are again going to get 0, because after all applying any operator on the zero vector will get you again 0. On the left hand side, this operator will get cancelled with its inverse, and we will be left only with v t to the power s minus 1. So instead of writing all those things, we simply write hence, because it's understood what we have done. If we next write this, it's understood that we have applied the inverse of this operator, this combination, on both sides. But now something will go wrong. Now you recall what S was. S was the first index such that alpha S is non-zero. Fine. But what was the range of S? I mean, where did S lie? S lies in this range, right? Because those are the indices that are available to us for indexing the alphas. We start from alpha 1 and we end at alpha n1. So S is less than or equal to n1. Since S is less than or equal to n1, we have, so now what we do, let me write what we are going to do, let me just write that. We can apply this operator on both sides of this equation. Where is this inequality playing a role? It's playing a role in the fact that we are having a non-negative exponent here, non-negative integer, and that is why this power makes sense. Remember, having a negative integer will likely cause a problem. Why? Because a nilpotent operator will not be invertible. So for example, instead of a non-negative integer here, say you have -1. What will this power then mean? It will mean the inverse of t, which may not exist. And that is why we need this non-negativity. And also do not confuse this situation with group theory. In group theory, you can take any integral power of an element of any group. That's because in a group, all elements have inverses. That's not the thing here. With respect to multiplication, an algebra is not in general means it's not a group. Okay, that's why we need this condition. But then this implies what? When you compose these two operations and use the rules of exponent, you see, in spite of not being a group, in an algebra, in fact, in any ring, you do have the rules of exponents when the powers make sense. Okay, so that's why you can add these two exponents and have this. On this side, of course, you are going to have 0. Applying any operator on the 0 vector will get you 0. But this is not correct, right? Because we chose V in such a way that this is not 0. So this goes against the very choice of V. This is a contradiction. So our supposition is wrong. Which means what? What was our supposition? That all the alphas are not 0, which thus has to be wrong. That means all the alphas actually are 0. And that actually proves our claim. So, or instead of writing like this, which is a little not accurate, let me write like this. Hence, the claim that those vectors are linearly independent over F. All right. Okay, now what are we going to do with this linearly independent set? We are going to span a subspace of V with them. Oh, and by the way, how many vectors were involved? Let us recall what the vectors were: V, Vt, Vt squared, and so on up to this. If you start counting from the second one, you get n1 minus 1 vectors. And then you count this one also, so you have n1 linearly independent vectors. So they are going to span a subspace of dimension n1. Okay, because this will be basis vectors for that subspace. So let V1 be the subspace of V spanned by these vectors. Then dimension of V1 over F is n1. Also, there is something else about this subspace. V1 is invariant under T. But how? V1 is invariant under T means that if you take any vector from V1, apply T on it, then the result will again be in V1. Now, we do not have to take an arbitrary vector from V1 to see that. If T does not get us outside of V1, when you apply T on the basis vectors, that's enough. Okay. Is that true? Let's just see. Let us take the basis vectors of V1 one by one, which are just these vectors, and apply T on them. If you take V, apply T on V, what do you get? Vt. On Vt, if you apply T, you get Vt square. So you are not going outside V1, you are staying inside V1, and like that, you go on getting vectors from here only. If you apply your T on the vector before this one, then you are going to get this one. But what happens when you apply T on this last one? Will that take you outside of V1? Let us see. You apply T on this. Composing this power of T with T, you get this. So what is this? This is the zero operator, right? Because T to the power n1 is 0. So V0 is 0. And of course, 0 is in the subspace V1 because it's the 0 vector. So no, you do not get outside when you apply T on these vectors, basis vectors. So automatically, on any vector of V1, which are just linear combinations of these basis vectors, also when you apply T, you do not go outside of V1, you stay inside V1. And that is why V1 is invariant under T. And because of how the vectors are in this basis for V1, you will notice that if, well, let me just write the sentence first and then we will see how that is true. Moreover, if T1, although this is not something that you will find in the book, I am just simply giving it a name, okay. If T1 is the operator on V1 induced by T. Because V1 is a subspace of V, you can restrict your original operator T to V1. And because again V1 is invariant under T, so this restriction which we are calling T1 will take you from V1 to V1 again, and in fact it will become an operator on V1. Then the matrix of T1 with respect to the above basis. Above basis means this basis is Mn1. That's how we get the first diagonal block of our total block diagonal form. I am not going to say how this is Mn1. I just simply ask you to apply T1, which essentially is nothing but T, on these basis vectors and write the equations. From those equations, you will be able to write the matrix. You will see that the matrix is in fact Mn1. Okay, it's just a matter of verifying. There is no twist, nothing complicated in this. So it's just a fact which happens. So I leave this to you to figure out, to just see how it comes. And the proof abruptly stops here, and after that the author makes a claim in the form of a lemma, and then the lemma is proved. So let's see what that next lemma is. We are not going to prove it today though. It's a psychological thing actually. You see, when we encounter long proofs, if we divide the proof into parts and give the, dividing a long proof into parts by itself won't do anything, because after all you have to go through the entire proof. But if you give those parts some names, it seems as if you are doing different jobs. So you complete this much, then you take some rest, then you do the next part which has a name. Like that, if you think, you won't feel any burden on you. It's just a psychological thing. So the next lemma is this. So what I am saying here is that there was no need for giving it a name like lemma this or lemma that, but you have that psychological advantage. As if you have completed something and you are starting something new. Alright, so what have we done so far? We have got a subspace of V, which we are calling V1, that turns out to be invariant under T. And it turns out that when we restrict our T on V1, then the matrix of the restriction, that restricted operator, with respect to that specific basis which we had here, is in fact Mn1. Now the claim is that besides this subspace V1, there exists another subspace of V which is also invariant under T, such that our original V is the direct sum of these two subspaces. That is this lemma. And that lemma, the statement is just this. There exists a subspace W of V invariant under T. such that V is the direct sum of V1 and W. So we are going to see the proof of this, which won't really be that and not as straightforward as this one. But we will see what it has and what its several parts are, not today, in the next video. So I am just going to stop here itself. I don't exactly remember what we have tomorrow, but we have something tomorrow, either a video or a community post. So anyway, that's just it for tonight. See you tomorrow. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.